Hello everyone, welcome back to the channel. Today, we're diving deep into one of the most foundational and fascinating concepts in natural language processing, word embeddings and contextual representations. We'll explore what these embeddings are, understand the critical difference between static and dynamic embeddings, and walk through popular models like Word2Vec, Glove, Elmo, and BERT. And finally, we'll learn how to visualize these high-dimensional vector spaces to build better intuition. So buckle up. This is going to be an exciting journey. Let's jump right in. So let's start with the basics. What exactly are word embeddings? Word embeddings are numerical vector representations of words that are specifically designed to capture their semantic meaning. Now, you might ask, why do we need this? Well, traditional NLP methods used something called one-hot encodings. These were simple binary vectors, but they had a huge problem. They were sparse and completely incapable of capturing any similarity between words. Word embeddings solve this beautifully. They transform words into dense, low-dimensional vectors, typically 100 to 300 dimensions, so that words with similar meanings end up close together in this mathematical space. For example, the words king and queen will get vectors that are very close to each other, enabling machines to understand their relationships mathematically. Pretty cool, right? Let me show you this visually to really drive the point home. On the left, we have one-hot encoding. Look at this. King is represented as 1, 0, 0, 0, and so on. The problem? These vectors are massive, as large as your entire vocabulary, which could be hundreds of thousands of words. And worse, every word is equally distant from every other word. There's zero understanding of meaning or relationships. Now, on the right, we have word embeddings. Same words, but now represented as dense vectors like 0.8, 0.6, minus 0.2. Notice how king and queen have similar values? That's because the model learned they're semantically related. Embeddings are dense, only 100 to 300 dimensions. They capture semantic meaning, and similar words naturally cluster together. This is the power of embeddings. Now let's talk about our first category, static embeddings. Static embeddings assign the same exact vector to a word regardless of what context it appears in. The most popular static embedding models are Word2Vec by Google and Glove by Stanford. Word2Vec works by looking at the surrounding words, we call this a context window, in sentences, to learn embeddings. It has two main approaches, CBOS, which stands for Continuous Bag of Words, and Skipgram. Here's the key thing to understand. These embeddings are fixed after training, so the word bank in riverbank and savings bank gets the exact same vector. They're treated identically. So what are the benefits? Static embeddings are super efficient, fast to train and use. They're incredibly effective at capturing semantic relationships, like that famous example, man is to king as woman is to queen. But the limitation is obvious. They cannot differentiate word meanings based on varying context. This is a major issue with polysemous words. Words that have multiple meanings get averaged into one confusing representation. Let me show you how simple it is to work with Word2Vec in Python using the Gensim library. First, we import Word2Vec from Gensim. Then, we prepare our training data, which is just a list of sentences, where each sentence is a list of words. We create the model by calling Word2Vec, specifying our vector size, let's say 100 dimensions, and our context window size. Once trained, getting a vector for any word is as simple as calling model.wv kink. This returns a 100-dimensional NumPy array. And here's something really cool. We can find similar words using most similar. And remember that famous vector arithmetic? King minus man plus woman equals queen. We can actually do that. Just use the positive and negative parameters. I'll put this complete code in the description so you can try it yourself. Let's take a moment to weigh the pros and cons of static embeddings. On the benefit side, they're efficient, low memory footprint, fast to infer. They capture semantic relationships beautifully. Those vector arithmetic examples actually work. And they're easy to integrate, just a simple lookup table. But the limitations are significant. There's no context awareness. Bank is always bank, whether it's financial or geographical. This is the polysemy problem. Multiple meanings get averaged into one confusing representation. And once trained, they're fixed, can't adapt to new dements.
This brings us to the game changer, dynamic or contextual embeddings. Dynamic embeddings generate different vectors for the same word depending on its sentence context. Let me show you what I mean. Look at these two sentences. The bank of the river is beautiful, and I went to the bank to deposit money. With static embeddings, bank gets the same vector in both. But with dynamic embeddings, we get vector 1 for the first sentence, which is related to concepts like shore, water, and nature, and we get vector 2 for the second sentence, related to money, finance, and institution. Vector 1 does not equal vector 2. The model actually understands the context and adjusts accordingly. This is revolutionary. ELMO, which stands for Embeddings from Language Models, was a breakthrough in 2018 from Allen NLP. ELMO uses a deep bidirectional LSTM trained on language modeling. Let me break down what makes it special. First, it's bidirectional. It reads text both left to right and right to left simultaneously, giving it full context. Second, it's character-based, which means it can handle out-of-vocabulary words it's never seen before. Third, it combines representations from all LSTM layers, giving you rich, multi-level features. The result is context-sensitive embeddings that capture both syntax and semantics at different layers. It was a significant leap forward from static embeddings. But then came BERT, bidirectional encoder representations from transformers, and it changed everything. BERT takes contextual embeddings even further, using transformer architecture and something called masked language modeling. Here's how it works. BERT randomly masks words in sentences and tries to predict them using the full context, both left and right simultaneously. Unlike ELMO's sequential LSTMs, BERT's transformer uses attention mechanisms to capture long-range dependencies efficiently. For example, if we give BERT the sentence, "The cat sat on the mask," it uses the entire sentence context to predict likely words like mat, floor, chair with remarkable accuracy. BERT embeddings are truly dynamic and have become the foundation for state-of-the-art performance across virtually all NLP tasks. Let me show you how to extract contextual embeddings with BERT using the Hugging Face library, which, by the way, has made working with these models incredibly easy. We import BERT tokenizer and BERT model from transformers. Then we load a pre-trained BERT model, in this case, BERT base uncased. Now, let's take those two sentences with bank again. We tokenize each sentence and pass it through BERT. What we get back is last hidden state. These are the contextual embeddings. Notice the shape. It's 1, sequence length, 768. That 768 is the embedding dimension for each word. The key point, the embedding for bank in sentence 1 is different from the embedding for bank in sentence 2. That's the power of contextual embeddings. Let's put everything together with a comprehensive comparison. Context sensitivity? Static embeddings? No. Dynamic? Yes. That's their whole purpose. Same word, same vector? Static? Always yes. Dynamic? No. It depends on context. Model complexity? Static embeddings are lightweight and fast. Dynamic embeddings use transformers. They're heavyweight but powerful. Training data? Static models need millions of words. Dynamic models are typically trained on billions of words from the internet. Inference speed? Static is lightning fast, just a lookup. Dynamic is slower because it needs to process the full context. Use cases? Use static for basic semantic search and feature extraction. Use dynamic for complex tasks like question answering, sentiment analysis, and language understanding. Now, here's the question. These embeddings exist in 300 or even 768 dimensions. How do we actually see them? How do we build intuition? This is where dimensionality reduction comes in. We use techniques like t-SNE and PCA. t-SNE, T-distributed stochastic neighboring embedding, preserves local structure. It's fantastic for visualization because it shows clusters very clearly. PCA, principal component analysis, is a linear technique. It's faster than t-SNE and preserves global structure better. Both of these compress our high-dimensional vectors down to 2 or 3 dimensions so we can plot them on a simple 2D graph. The key is that they preserve relative distances, so similar words stay close together.
So what do these visualizations actually show us? First, semantic clusters. Look at this. King, queen, prince, princess. All royalty words clustering beautifully together. And here's another cluster. Car, taxi, vehicle. All transportation concepts. But notice the separation. The transportation cluster is far away from the fruit cluster with apple, orange, banana. This is semantic distance in action. Different categories of meaning stay far apart in the vector space. This is incredibly powerful for understanding how our models see language. Let me show you the exact code to create these visualizations. First, we load pre-trained Word2Vec vectors using Gensim's Downloader API. Then, we select a list of words we want to visualize. Let's include some royalty words, fruits, and finance terms. We extract the vectors for all these words. That's our 300-dimensional data. Now comes the magic. We use t-SNE to reduce from 300 dimensions down to just 2. We call fit transform and boom, we have 2D coordinates. Finally, we plot using Matplotlib. For each word, we plot its 2D position and annotate it with the actual word text. Run this code and you'll see those beautiful clusters I showed you earlier. It's amazing to actually see the semantic relationships the model learned. You might wonder, why go through the trouble of visualizing? Well, there are 6 powerful reasons. Debug. You can identify if your embeddings are actually capturing the relationships you expect. Intuition. You understand how your model sees and represents words. Analysis. You might discover unexpected patterns or even biases in your embeddings. Education. It's much easier to explain to stakeholders what your model is doing when you can show them visual clusters. Validation. You can verify that your training actually worked and converged properly. And exploration. You can find interesting semantic relationships specific to your domain that you might not have expected. Now, let me show you one of the most mind-blowing properties of word embeddings. Vector arithmetic. King minus man plus woman equals queen. Think about this. We're literally doing math on words, and it captures gender relationships. This isn't programmed. The model learned this just from reading text. Paris minus France plus Italy equals Rome. It learned geography. Walking minus walk plus swim equals swimming. It learned grammar transformations. Bigger minus big plus small equals smaller. It learned comparative forms. What this really means is that embeddings encode semantic relationships as geometric relationships in vector space. Similar concepts have similar directions. This is absolutely magical. So why are dynamic embeddings the future of NLP? Number 1, context-aware understanding. They capture subtle meaning shifts that static embeddings completely miss. Number 2, better performance. They achieve state-of-the-art results across virtually every NLP benchmark. Number 3, transfer learning. You can pre-train once on massive amounts of text, then fine-tune for any specific task with minimal data. Number 4, they handle polysemy beautifully, correctly disambiguating words with multiple meanings based on context. And number 5, rich representations that capture syntax, semantics, and pragmatics all at once. And here's the thing, dynamic embeddings are the foundation of modern NLP. GPT, BERT, T5, and all the latest language models you hear about, they all build on these principles. Let's talk real-world impact. Where are these embeddings actually used? Chatbots, understanding user intent and maintaining context across conversations. Search engines, Google and others use embeddings for a semantic search that goes way beyond simple keyword matching. Translation, context-aware machine translation that actually understands nuance. Sentiment analysis, understanding not just what people say, but the emotions and opinions behind it. Question answering systems like the ones that can read a document and answer specific questions about it. And text generation, creating human-like content, summaries, even code. These embeddings are literally powering the AI revolution happening right now. Let me tie everything together with one final code example that directly compares static versus dynamic embeddings. We load both Word2Vec, our static model, and BERT, our dynamic model. We have 2 sentences with the word bank in them in different contexts. With Word2Vec, we simply get the vector for bank, and it's the same regardless of which sentence we're thinking about. But with BERT, we create a function to extract the embedding for bank at its specific position in each sentence. And when we calculate the cosine similarity between these 2 BERT vectors, we see they're different. This concrete example shows exactly what we've been talking about. Static is context-blind, dynamic is context-aware. Let's recap the key takeaways from today's tutorial. Number 1. Static embeddings, like Word2Vec and Glove, assign 1 vector per word. They're fast and efficient, but completely context-blind. Number 2. Dynamic embeddings, like Elmo and BERT, create context-aware vectors that capture nuanced meanings and handle polysemy. Number 3. Visualization with t-SNE and PCA helps us understand and debug embeddings intuitively by seeing semantic relationships in 2D. And number 4, dynamic embeddings are the future. They power modern NLP systems and are the foundation of models like BERT and GPT. If you want to dive deeper, I've listed some essential resources here. Read the original papers, Word2Vec from 2013, Glove from 2014, Elmo from 2018, and BERT from 2018. These are foundational papers every NLP practitioner should know. And check out the Hugging Face Transformers documentation. It's an amazing resource. As for next steps, install Gensim and train your own Word2Vec model. Use Hugging Face to load and experiment with BERT. Create t-SNE visualizations of your embeddings. And if you're feeling adventurous, fine-tune BERT on your own dataset, or even build a semantic search engine. Comment below and let me know what project you want to tackle first. And that's a wrap. We've covered everything from the basics of word embeddings to the cutting-edge contextual representations powering today's AI. You now understand the difference between static and dynamic embeddings, how models like Word2Vec, Elmo, and BERT work, and how to visualize these vector spaces to build better intuition. If you found this valuable, please hit that like button. It really helps the algorithm show this to more people. Subscribe if you haven't already, and ring that bell so you don't miss future tutorials. And drop a comment below. Let me know what NLP topic you want me to cover next. Thank you so much for watching, and I'll see you in the next tutorial. Keep learning, keep building, and I'll catch you later. Bye.